Bonds. Chemical bonds. But first, Mr. and Mrs. Bond. Retired British secret agents have to go somewhere. At least 2 ended up in the Witness Protection Program in the bucolic Central Valley of California, posing as teachers. A job only slightly more stressful than being a secret agent. It can be a tough adjustment.
My name's Bond. Ionic Bond.
Even coming home from work, you can't be too careful.
Nice enough fella, but I think he's wound about 3 turns too tight.
Okay, let's turn to chemical bonds. Atoms form bonds to achieve some sort of more stable electron configuration. All atoms want the stable low energy configuration of a noble or inert gas. Nature prefers a high level of entropy or disorder, stability. This can be managed for most atoms by giving away electrons, taking another atom's electrons, or sharing electrons to make a bond. All this is done to have that stable octet of 8 electrons in the valence or outer shell of electrons. To look at this, we need to consider electronegativity, which is a measure of how strongly an atom holds on to electrons. The atoms in the upper right-hand corner of the periodic table have the highest, the lower left the lowest. Here we show fluorine with a 4.0 as the highest in electronegativity, and the lower left-hand corner elements being the lowest. The amount of difference in electronegativity between the 2 atoms bonding determines what kind of bond occurs between them. Generally, a large difference comes up with an ionic bond. In between is a polar covalent bond, and no difference is a nonpolar covalent bond. Here, let's look graphically at how electronegativity and bonding goes together. For an ionic bond, the difference in electronegativity would be between 3.3 and 1.7. The in-between polar covalent would be down to 0.3, and nonpolar covalent would go down to no difference in electronegativity. Let's look at percent ionic character, another way of judging that. Anything above 50% ionic character is ionic, all the way down to 5% is polar covalent, and 0 is nonpolar.
Honey, I'm home. So covalent, how was your day today?
Crikey, cheeky kids today. I bloody well thought I would be barmy by 3 o'clock. So I chuffed to get home early, care for a spot of tea.
Ooh, that would just be the bee's knees. Oh, thanks, that's just ace.
Let's look specifically at ionic bonds. Ionic bonds involve atoms completely losing or gaining electrons to then take on a positive charge, loss of electrons, or a negative charge with the gain of electrons. This type of bond holds huge numbers of cations and anions together because of their charges in a 3-dimensional structure. Imagine all of these cations and anions all mutually being attractive. This 3-dimensional crystalline structure of atoms having ionic bonds is why you think of a chemical formula like NaCl, table salt, as a formula unit, representing the lowest whole number ratio, 1:1 in this case. How could you say which cation belongs to which anion? It doesn't work that way. Recalling electronegativity, it makes sense the group 1 and group 2 would lose electrons to become positive ions. With its higher electronegativity, the right side of the periodic table tends to gain electrons.
Shaken, not stirred.
And your day?
Well, the morning was just tickety-boo. But by fifth period, they seemed totally gormless about chemical bonding. I couldn't believe it. And I was really cheesed off about sixth period. They tried to faff about for half the period and think that I would go for it. I'm not that mug.
Okay, generally, how do ionic bonds form? Here you have sodium atom with 1 valence electron, chlorine with 7. Now, if chlorine was to gain 1 more electron, it would have an octet in its valence shell, and sodium would go back to the lower energy level and also have 8 valence electrons. So with protons not changing, that means chloride ion takes on a -1 charge, sodium +1. Again, remember this attraction takes place in 3 dimensions.
If only I had another electron, I would feel complete.
Okay, go ahead.
So how are covalent bonds different? Covalent bonds see atoms sharing electrons so that both atoms can be surrounded by that octet of electrons. Although electrons might not be completely gained or lost as in ionic, atoms' differences in electronegativity may see them sharing evenly or unevenly. As an example of a covalent bond, 2 chlorine atoms share valence, outer shell electrons, to get a noble gas-like electron configuration. Here's 2 chlorine atoms, each having 7 valence electrons. No difference in electronegativity. If they share those electrons, each will have an octet around it. This is where electrons are shared equally because of the no difference in electronegativity, so it's nonpolar. We'll talk about that more later.
I think little electron likes you better than she does me.
Let's look at polar covalent bonds. Polar, like the poles of a magnet. One end of the molecule has at least a partial positive charge and the other has at least a partially negative charge. Here's a polar covalent bond between oxygen and hydrogen with 2 shared electrons. But it's an uneven sharing of electrons. Oxygen is more electronegative than hydrogen, so it has more of a pull on those shared electrons than does the hydrogen. This sees the electrons being more attracted to oxygen, so that when you think of this bond, this sharing of electron cloud, the oxygen end has the shared electrons more of the time, so it's negative on that end, and hydrogen has a deficiency of electrons, so it's positive. And now the nonpolar covalent bond. Like we did with chlorine, we'll take 2 of the same atom, hydrogen, where the electronegativities again are exactly the same. Each end of the molecule has the same charge, therefore there is no positive or negative pole to the molecule, which gives you evenly overlapped electron clouds. Let's review. Electronegativity and other factors control to what degree atoms give up, take up, or share electrons to form lower energy, more stable situations that we call chemical bonds. These bonds run from the complete exchange of electrons in the ionic bond to the even sharing of electrons of the nonpolar covalent bond. The polar covalent bond is somewhere in between the two.